Hello guys, welcome back to the LearnRISC-V channel. And in this session, I'm just gonna talk briefly about the atomicity in RISC-V. So in RISC-V, this atomicity instructions are categorized into two groups, or I would say that there are two forms of atomic instructions in RISC-V. One is the load reserved and store conditional, which we are not gonna see in this session, but I would cover that in another session. Whereas in this, I'm just gonna talk about one of an AMO instruction. AMO stands for atomic memory operation. So there are more than one atomic memory operations, but just discussing one would help you to understand the rest of them all. Okay, so if you would have watched the previous video or one of my previous session where I used UART to transmit and receive the data back through by looping the UART TX and RX pin. So this is the code which was there in the UART send byte function. So what it basically does is, so this loads the memory mapped address of the UART1 TX register, and then it would read status. So if you see the description of the UART TX register, it has 3 segments. The last 8 is the data that has to be written to transmit the data, and rest all except 1 is reserved, and the MSB are the most significant bit. If you read, that would give the status of the FIFO, if the FIFO is full or if there is a space in the UART FIFO. So if the FIFO is full, then any write into that TX register would be just ignored, and it's very difficult to know if the data has been transmitted or not unless you get a feedback from the receiver end. So in the code which I used for the loopback exercise, I would just read first the UART1 TX register and see if this status is, if the FIFO is full or not. If it is full, then this function would just return a 1 in A1 register, which I validate and check before sending, just to decide if the data has to be sent again or not. So this is how the function was, at least. Okay, so if you see here, this is, so that means that it was working, and you can't find anything wrong in this because this is the best that it can do. Read and check if there's a space in the FIFO, and if there's a space, then if you see here, it will write back. But if there is no space, if the FIFO is full, then it will come back and it will set this A1 as 1, and it will return, so that when it returns to the caller can check if there is an error. Okay, then it can try to send again. Okay, but let's if you look carefully into this entire function can be just broken down into two things. One is like read the FIFO status if it is full or not, and then just a memory write. I call this as a memory write because this is a memory mapped register. Okay, so these are the two operations, or this can be broken down into this simple 2 operations. Okay, so now on a single threaded application, or the one which I demoed in the previous video, it was just one application in which this UART loopback application would just keep sending this. If this FIFO is full, it will just go back and start reading it, and vice versa. Okay, so this is how it would be in a single threaded, and please be aware that RISC-V standards does not say anything about the implementation of any of these instructions. All it would say is like how this instruction should work, and it doesn't put any constraints or restrictions on how that should be implemented. Okay, but let's take an example of a DLX pipeline or other. So a simple processor with the simple pipeline. So this is the most simplest pipeline, like instruction fetch, decode, execute, and write back. I don't know if there can be any simpler pipeline. So on a single threaded with a single threaded application on this simple instruction pipeline, so this is how these instructions would be pushed into the pipeline one after the other. So the first, when the read full status instruction goes, the next would be in this decode stage, and so on. And as you see, so there is no way that this read full status or anything can be anything would go out of order, or I don't see any problem in this as working. Okay, so this should fairly work. So what happens when we have a multi-threaded environment where there are multiple threads? So let's take an example with 4 threads. So each color represents a thread, and so each thread, as I said, that it's not uncommon that most of the threads would use UART, because for any debug logs or any printouts, all those messages go through the UART. So it's very common that most of the threads would be accessing UART very frequently. So each thread, as I broke it before, let's just break that function to read full status and then followed by a memwrite. So that would be a sequence of these instructions from each of these threads, and this has to be fed into the pipeline. So, and it has to go to the pipeline, and then at the execute and write back stage, this goes into so this value should be written into this memory mapped address, and that would go into the FIFO, and from the FIFO it would be pushed into the UART TX pin. Okay, so this full status is the status of this 8 FIFOs in UART. This example is for FE310 ISOC. And this FIFO is also configurable. You can just say that you want to use FIFO of just one, FIFO length of just 1, or all the way up to 8, I guess. Yeah, you can configure that. So if you just configure as 2, then once there are 2 bytes enqueued, then the FIFO status would show full. Okay. So now let's come back to this instructions being pushed into this pipeline. So in the previous single threaded application, you would there's no possible way of this going out of order, whereas in this multi-threaded, this is very this can easily happen. Like if you see just match the colors. So this read full status of thread 1 is here, and before the memwrite, so let's say that this read full status from thread 1 returns that there is a FIFO space available or the buffer available, but then before this memwrite comes, it can switch to thread 2, and thread 2 would have already read the full status, and it might have written a byte to it. And then when this thread 1 memwrite is inserted into the pipeline, and if there is only one, if it is configured only for one FIFO, there's a very good chance that this memwrite would fail. But the worst part is that as long as you don't get any feedback from the receiver, it's very difficult to know if this write has been successful or was it dropped. So if the FIFO is full, any write into this TX register would be just dropped. Okay, so that's how it would be if there is no atomicity, or it would be really hard on a multi-threaded environment. So there are many ways that you have to do on the software side to ensure that these don't happen. There are ways on it, but in RISC-V, that is, if the core has the atomic instruction extension, we call that as A. So as you know that in RISC-V, the instruction set has multiple extensions like M for multiply and division, and you have A for atomic extensions. And this A has, as I said before, there are two forms. One is the load store and load reserved and store conditional, and this one is the AMO or atomic memory operation. So we will see about this one particular atomic memory operation. So this is OR operation. So atomic memory operation, bitwise OR on a word that is like 32 bits. And this is the syntax. So you have three operands. So let's see what would this do. Okay. So this RD is a destination register, and RS1 is a source or the memory mapped address or memory address, let's say that. So with this UART example, so this memory mapped address, so if you feed the memory address or the memory mapped address of the TX register in RS1 and RS2 with the value that has to be transmitted, let's say that we want to transmit hex 24 through UART TX, and that value is in RS2. So what would this instruction do is this RD, you can choose one of the register. So this instruction would very first read from this memory address, whatever the value there, it would read, okay, and then it would perform a bitwise OR operation on with the value in RS2, and the result or the output of the bitwise OR operation would be written back into this memory address. Okay, so that's a lot of operations, but this all this whatever happens in this a dashed lines box, all this happen atomically, like one atom. It's not broken down into multiple steps or anything. So let's now see how this helps and how this solves the problem. Okay, so first, whenever since this is a TX register, reading a TX register as per the manual, it would just reading a register would return 0 except the status of the except the full status bit or the except that MSB. So let's switch to the, if you see the manual here, so reading from the TX data returns the current value of the full flag, so which is nothing but the 31st bit position, and 0 in the data field. Okay, so going back, so the read can only have two values, which is like either all zeros or it can be 8 followed by all zeros, or the most MSB can be 1. So that means that either the FIFO is full or there is space. That's it. So that value can be read, and then it's a bitwise OR, so that this whatever the data we have to transmit gets into the last 8 bits, and then it's returned back. Okay, now after writing back, then if you check the MSB bit, and if it is full, or if the bit is 1, that means for sure this byte is dropped. Okay, and if this is 0, that means that this byte has been written successfully and transmitted through UART. Correct. So that's the use of this AMO OR, and this is one example on how to use this atomic memory operation to transmit data through UART without any data loss. Okay, so what this AMO instruction has done is that it has coupled or grouped the read full status and memwrite as one single instructions, which cannot be broken down further. That's it. Okay, so now so this cannot be broken, but as I mentioned before, if the sender wants to know if the data has been sent or not, it's very simple. So after performing this operation, or after this one instruction, in the next instruction, if the RD value, I think it's in the RD, yeah. So the result, if you just get the MS most significant bit after this operation, and if it is 1, for sure this is a drop. So it also helps to find out exactly if the data is dropped or it is sent. Okay, hope that helps. And if you see the RISC-V unprivileged spec, and this is the A extension, which stands for atomic. As I mentioned, AMO is the atomic memory operations. Similar to bitwise OR, you have AND, exclusive OR, and there is also arithmetic and swap. And this is the first form, which we would cover in another session, which is the load reserved and store conditional. Okay, now if you go back to this, and you would be able to easily follow that. And this is the code I used for UART loopback, and this is what I used in the discussion now. Now, instead of all this, I can just use this one instruction and replace this bunch of instructions, and still it should work. Okay. Thank you, and see you in the next session.